All right, hello. Today we're going to talk about empirical probabilities. We've been doing a little bit with counting and sort of theoretical situations, but this is going to be more real world. So we're going to look at probability of one event and another event, um, one or another, and mutually exclusive and non-mutually exclusive events. So we're going to talk about those things. But first, we're going to talk about empirical probability. That's used in situations where we observe how frequently some event occurs. So we're talking about using real world data. Okay, not theoretical things, but actual things, and then we can collect data, and then we can analyze the data, and we can make predictions based on that data. And so how do we do that? Well, the probability, so we have the empirical probability of an event E. We're going to use this notation right here. Probability of event E is the observed number of times that E occurs divided by the total number of observed occurrences. So, and I think you're mostly familiar with probability. This shouldn't be a super new idea. So we're going to start with this situation about, take a look at the table and see if you can get your brain around it. Maybe pause the video, take a look at the table, and then we'll come back. Okay, so this is about the hours of sleep for Americans, and our numbers are in millions. So those are all things you want to think about. So what is the probability of an American getting 6 hours of sleep a night? So what we need is the observed value. 75 million Americans got 6 hours of sleep a night. And then we're going to divide that by the total number of Americans that they observed, which is 300. And that right there is a probability. You can give probability as a fraction. You can also calculate this. Like I could reduce my fraction. 75 goes into 300 4 times. We can also write it as a decimal. That would be 0.25. Or again, sometimes people write probabilities as a percent, and 0.25 would be 25%. Those are all acceptable ways of writing that probability of an American getting 6 hours of sleep a night. For the next one, we could talk about what's the probability of getting 8 or more hours of sleep a night. So this time I have more than one piece of data that I have to sort of add up. 8 or more. So this is included in 8 or more. This is included in 8 or more. Those are all included in our 8 or more hours of sleep a night. So we're going to have 81 million plus 9 million, that's 90, plus 6 million over 300 million. So 96 out of 300. And if you do the math, you could get 0.32, otherwise known as 32%. So 32%, or almost a third of people in the US typically get 8 or more hours of sleep. If it just said more than 8 hours, we wouldn't have included the 81. It just would have been the 9 and the 6. What's the probability of fewer than 10 hours of sleep a night? So let's have you pause the video for a second and see how you want to approach that problem. So one way to approach that is to add up all of the data about that's less than 10. So basically everything other than the last bit. But an easier way to do this is to kind of go what I call going through the back door. And going through the back door says, well, I know that there's a total of 300 and I want everybody but 6. So that's going to leave, actually it's going to be 294 out of 300, or approximately 98% of people. And that's the back door. Instead of adding up all the numbers and then taking that out of 300, I can subtract what I don't want from my total of 300, and that's how many are in what I do want. Which leads us to some ideas about probability. If something is impossible, what is our probability? If something always happens, what is our probability? What kind of values do we get for probability? And if something, the probability is P of E, then the probability it won't happen is what? So see if you can fill these out on your own. Stop the video. If we look at this, if something is impossible, we have 0 chance. If something always happens, our probability is 1 or 100%. So a probability as a decimal is always between 0 and 1. As a percent is 0 to 100%. And then if the probability of something happening is P of E, then the probability it doesn't happen is you take 100% and you subtract the probability that it doesn't happen, and that's the probability that it will happen. Or that it won't happen. So the probability it won't happen is 1 minus the probability that it does happen, which is that backdoor problem that we had, right? We had 100% minus 6 over 300, and that gave us our total of 294 over 300. All right, so here's another situation. I find this one fascinating. So it's a time breakdown for average 190-minute NFL TV broadcast. So they have different sorts of, they've broken down how many minutes are spent for each thing. So take a look at that and then see if you can answer the question, what is the probability that a minute of the broadcast is not devoted to game action? So again, I could add up all of the parts, or I think this is another one that sets it up itself up beautifully to go backdoor. So I could do, there's a total 190 minutes. So that's like my 190 minus 190. That's my 1. And then not to game action is 1 minus game action. And the game action is only 11 minutes, which leads us with 179 out of 190, or 94%. That's sort of amazing to me. So 94% of that 190 minutes is not spent on game action. I mean, I guess theoretically you could say replays are game action. So even if we did that, we could try 190 minus 26, and we could get a different probability. That's still not a whole lot of the time you spend is actually watching game action. Okay, we have another situation. Looking at women ages 40 to 50 in the US, and we're looking at mammograms and how that relates to breast cancer and no breast cancer. So again, what's the probability that a woman aged 40 to 50 has breast cancer? So what I need to do is I need to find all of the women who have breast cancer. So I'm going to add up these two columns, and I get 800. And then I need to know the total number of women, which, they said is 100,000. And so my probability is the outcomes that we're looking at, which is having breast cancer out of all of the people surveyed. And we get approximately 0.008, otherwise known as 0.8%. So luckily, not super high. So now we're going to look at sort of narrowing it down. We have this table with all this data. We can narrow it down among women without breast cancer. So we are only going to look in this column right here. So among those women, find the probability of a positive mammogram. So our positive mammogram, that's our top of our fraction, is 6,944. And then I need the total there, and if you add up these two numbers to get the total down here, that total turns out to be 99,200, and we get a probability of about 7%. Okay, but I'm in that one column of We are among women without breast cancer. So I'm limiting my total data set to just a subset. If I look at the next one, you should try the next one on your own and then see if you can get it. So pause the video. And if you're back, women with positive mammograms. So I'm looking this time not in a column, but I'm looking in a row. So among the women with positive mammograms, find the probability of not having breast cancer. So not having breast cancer, oops, is my top, and that's 6944. But this time, it's over the total of that row, and that row has a total of 7664. And we end up with 90.6%. So there, you can sort of, we have lots of different data, you can look at just pieces of it and analyze different pieces.